The next and the most important application of mole concept is in the stoichiometric calculations. Stoichiometric word means calculating the masses of the compounds which are involved in the reactions. It means we will be finding out the masses of the reactants and the products involved in the reaction. See, it's a very important to understand for any person who is studying chemistry, that how much of the reactant is to be taken to prepare how much of the product, or if this much of the reactant is taken, how much of the product is formed. Now all these calculations are called stoichiometric calculations, which are the backbone of all the reactions. Because industrially, whenever we are doing any reaction or we are into manufacturing of anything, we need to know that how much of the reactant are to be taken so that this much of the product is formed, or for forming so much of product, how much of the reactants are to be arranged, like so on. So it is not only the calculation of the masses, it is basically actually we are trying by this to we are using this stoichiometric knowledge, we'll be trying to complete a reaction. There is another important aspect of stoichiometry and the mole concept. Other than the masses, we can also use the same information of the mole concept in order to find out the volume of the substances. Suppose the product is not a solid, it's a gas. So how much of the volume of that particular gaseous substance is formed, that can also be calculated. Even we can also find out how many molecules or particles of that particular compound is formed, or how much of molecules or the particles of the reactants are required to prepare this much of this. So it is a very simple situations. The reactions are given to us, or sometimes the reactions are given in the form of the word problems. We have to write down the reaction, we have to balance them, and then we have to use the information of the mole concept. Like, let us take an example of Haber's process in which ammonia is prepared. In that particular reaction, nitrogen gas is reacted with hydrogen gas, which gives ammonia gas. Now in this, if you balance this, because this is not balanced, you have to balance this, it will be twice and it will be thrice. If we know our previous knowledge, if we will read out this reaction as one molecule of nitrogen reacts with 3 molecules of hydrogen to give you 2 molecules of ammonia. Whereas now, in terms of moles, we can read out this, that 1 mole of nitrogen reacts with 3 moles of hydrogen to gives you 2 moles of ammonia. And always these reactions takes place in these stoichiometric ratios, which are the coefficients written before the reactants in a balanced equation. I am repeating again, the reaction always takes place as per the stoichiometric ratios which are written before the reactants and the products in a balanced chemical reaction. So here it was only 1 nitrogen, so 1 mole, 3 hydrogens, so 3 moles, 2 ammonia, so 2 moles. So once we know that 1 mole of this nitrogen will be reacting with 3 moles of hydrogen in order to make the reaction complete, it is going to give us how much moles of ammonia? 2 moles of ammonia. Or for 2 moles of ammonia, how much of hydrogen is required? 3 moles. How much of nitrogen is required? 1 moles. Or for 3 moles of hydrogen, in order to have a complete reaction, how many moles of nitrogen is required? 1 moles. So like this. Another thing, in terms of molar mass, we can express the same information. We'll use now this basic mole concept here. We know 1 mole of nitrogen is 28 grams. 1 mole of hydrogen is 2 grams, but 3 moles here used, it means 6 grams. So 8 grams of the nitrogen requires how much grams of hydrogen? 6 grams of hydrogen. And when they will combine, they will produce what? Ammonia, whose 1 mole is 17 grams, 2 moles means 34 grams. So see, you can already see that the law of conservation of mass is followed. 28 plus 6 is 34 and this is 34. So now we can, if we don't want the information to be conveyed in terms of the moles, we can find out, we can convey this in terms of the mass also, that for preparing 34 grams of ammonia, how much of hydrogen is required? 6 grams. How much of mass of nitrogen required? 28 grams. Or how much of moles of nitrogen is required? 1 mole. Even we can convert the same thing in terms of the volume also. Like 1 mole of nitrogen is 22.4 liters. 3 moles of hydrogen will be 67.2 liters. And 2 moles of ammonia will be 44.8 liters. This is same information in terms of volume, and it has been converted from the same mole concept that 1 mole of a gas occupies 22.4 liters of volume at STP. See, now for preparing 44.8 liters of ammonia, how much of volume of the hydrogen is required? 67.2 liters. How much of volume of nitrogen is required? 22.4 liters. Or if we have 22.4 liters of nitrogen, how much of hydrogen is required completely to form, in order to make the reaction complete? It is 67.2 liters. So this is what is the information is, and we say that it is not only the mass relationship, it can be mass volume, or it can be volume mass, or it can be simply volume also. So these are the basics. Now let us understand the stoichiometry by taking certain examples. After understanding the importance of the stoichiometry, let us now do some numericals on this in order to understand how we can have a mass volume or volume mass relationship like this. Let us take the first example. Find the mass of water produced by the combustion of 8 grams of methane. So in this question, we are given 8 grams of methane which is combusted, and we need to find out that how much of water is obtained from this. Equation is not given to us, so we have to write down the equation on our own, and we have to then balance this. We already know from our previous knowledge that whenever a hydrocarbon is combusted in air, it gives only CO2 and H2O. Now, let us balance this equation. Carbon here is 1, so here is 1. Hydrogen here are 4, so we will make it 2. So this is how the oxygen becomes here 2 and 2, 4. So this is how it is balanced. Now from this balanced equation, we have to find, make out that in this numerical, methane has been correlated with water. Now what is the relationship in terms of moles we have between methane and water? See here, 1 mole of this gives you 2 moles of water. So 1 mole of methane gives 2 moles of water. This is the ratio, or we can say it's a molar ratio between these two components which are involved in this reaction. Let us find out how many moles of the methane are given. Now, moles of methane are its mass given by molar mass. It is 8 by 16, which comes out to be 2 moles. Sorry, it will be 0.5 moles. So we are given 0.5 moles of methane. Now let us use the stoichiometric relationship, which is this is that 1 mole of methane gives 2 mole of water. Therefore 0.5 mole will give 2 by 1 into 0.5, which is 1 mole of water. And 1 mole of water means, so therefore mass of water obtained is 1 into 18, which is its gram molar, its molecular mass or molar mass, so it will be 18 grams. So the answer is that the 8 grams of methane on combustion gives 18 grams of water. And this relationship we got from the balance equation, that they are related as 1:2. 1 mole of methane gives 2 moles of water. So if we are given 0.5 moles, so 0.5 moles will give you 2 by 1 into 0.5, which is 1 mole. 1 mole multiplied by its gram molecular mass will give you 18 grams. See, this is basically one condition which is given, which is actually is a standard which you get from a balanced equation, and one condition is given to us. So we have to put the given condition into the standard condition, then we can find out. There is another thing. This part is basically is your mathematics unitary method. So one has to be good in the unitary method in order to find out that how many moles of this are required or how many moles are formed. Let us do now one more numerical in order to understand the mass volume relationship. The numerical is find the volume of ammonia produced when 18 grams of hydrogen is reacted with excess of nitrogen. So see, the reaction is like this, that the nitrogen gas is reacted with hydrogen gas and it gives ammonia. Now we have to balance this. This is 2 nitrogen, 2 hydrogen. If you make it 2, this nitrogen gets balanced. The hydrogen is 6, so this becomes 3. Now what is important to note here is that 1 mole of nitrogen combines with 3 moles of hydrogen to give you 2 moles of ammonia. But in the numerical, we are given what? That we have to find out the volume of this produced from the 18 grams of this hydrogen, which is given. So we have to relate hydrogen and ammonia. See, the best way is, as per the stoichiometry, what is a molar relationship between hydrogen and ammonia? That 3 moles of this gives you what? 2 moles of ammonia. This is the molar relationship. Now let us find out how much moles of the hydrogen are given to us, so that we can then put this those number of moles into this relationship, which is 3:2. Now we are given 18 grams of hydrogen. So moles of hydrogen given are 18 grams upon its gram molecular mass or molar mass, which is 9 moles. So we are given 9 moles. So this is the standard one. Now we know 3 moles of hydrogen gives 2 mole of ammonia. When this 3 mole gives 2 moles of ammonia, therefore the 9 moles will give 2 by 3 into 9, 6 moles of ammonia. Now we know how many moles of ammonia will be formed. Once we know the moles of the ammonia formed, the mass of ammonia formed is 6 into 17, because 1 mole of ammonia is having 17 as a molar mass. So this will be in then grams, 2, so it's 102 grams. So this is how the mass can be obtained. Now, since the numerical was asking what is the volume of the ammonia formed is, it can be 6 into 22.4 liters at STP, because 1 mole will occupy how much of volume? 22.4 liters. So this will come out to be 134.4 liters. So if the numerical, as the numerical was asking to find out the volume, it is this much. If it asked how much of mass of ammonia obtained, simply multiply it by then its gram molecular mass. So this is the benefit of using the mole system in the stoichiometry, is that where whatever we want, whether the volume or the mass or the number of molecules, we can easily find it out. So this was a numerical which was actually correlating the mass volume relationship. Now let us understand the volume relationship by numerical. The numerical is find the volume of the CO2 produced when 5.6 liters of oxygen gas is reacted with excess of cyanamide, which is NH2CN. The NH2CN cyanamide, when combusted with oxygen, gives you nitrogen, carbon dioxide and water. The balance equation says 2 moles of this cyanamide combines with the 3 moles of oxygen to give you 2 moles of nitrogen, 2 moles of carbon dioxide and 2 moles of water. Now we are given oxygen. We are supposed to find out volume of CO2. What is the stoichiometric relationship between O2 and the CO2 is that 3 moles of oxygen gives you 2 moles of CO2. This is the relationship we have. Now we will use this stoichiometric relationship in finding out the volume of the CO2 which is produced from 5.6 liters of oxygen. Now let us first do the calculation of finding out the moles of the O2 given. See, the moles of oxygen given are 5.6 liters divided by 22.4 liters. This is 1 by 4, so it is 0.25 liters. Now, once we are given 0.25 liters, you must know this, that and 3 moles of O2 gives 2 moles of CO2. When 3 moles of O2 gives 2 moles of CO2, therefore 0.25 moles of O2 will give 2 by 3 of 0.25, which is 0.5 by 3 moles of CO2. Therefore, volume of CO2 produced will be 0.5 by 3, 22.4 liters. It will be 11.2 by 3, which will be approximately 3.73 liters. So this is how we got to know about the number of moles of the oxygen, which was 0.25. We were knowing 3 moles of oxygen is giving you 2 moles of CO2, so 0.25 will give you 0.5 by 3 moles of this CO2. Now, once we know the moles of the CO2 produced, simply multiply it by 22.4 liters, we get the net volume which will be obtained in the numerical.